So morning, everybody. Today we're going to do a lot of stuff that, wait, what just happened? Okay, so today we're going to actually look back at a lot of the things that we've spoken about and try to understand a little more about what happens inside the neural network. Now, what we've covered so far, we covered the basic idea of a little bit of the history, just to recap everything that we've done in the semester so far. We've done a little bit of history. We learned very early on that a neural network, in theory, can compute pretty much anything. Do you mind shutting your laptop, please? Yeah. So that in theory, a neural network can compute pretty much any function. And so the magical bit of that was that you could just connect up all of these seemingly trivial little units. And the moment you connected all of these seemingly trivial little units, they actually began doing magical things, like writing captions for pictures. We saw how we could actually connect these units up and make them do this magical stuff, like classify, predict, and put captions on pictures. We saw different kinds of networks. We saw simple multi-layer perceptrons. We saw convolutional networks. Convolutional networks are essentially just simple multi-layer perceptrons that scan data. And the idea behind convolutional networks was that you expect the data to have some kind of a repeating structure to it. So you can use the same network to scan it as opposed to having one complex network look at all of the data. We looked at recurrent networks, which can work with time series data. We saw how we could learn all of these things, the process of training, all the issues and pitfalls. And somewhere along the process, without even realizing it, while you were sitting there and cursing us out for giving you such a hard time, you actually became pretty proficient at training neural networks. And some pretty complex ones too, right? Think about it. Then finally, in the last class, until the last class, we sort of took the network structures for granted. They're just given to you. Someone gave them to you. You trained them. And then if you attended Scott's class, which I hope you did, you realized that there were ways of actually designing the network ground up in order to make them do exactly what it is you wanted to do. In all of this, while we got some high-level theory, and we got somewhat of a mechanical perspective of how to make these things work, there's one question that remains: what exactly do these networks learn? And we've seen a little bit of it early in the class. We're going to go back and revisit the whole topic all over again today. Now, and that is that's all it is. It's a very simple classifier slapped on top of a very fancy feature extractor. So let's go back and look at the very first problem we looked at. Here is the kind of problem that we actually addressed. You were given a collection of input-output pairs, illustrated by those red lines. And we had to learn the function that could predict the output value given the input value. So you had to learn this little mesh given just these input-output pairs. Now, if the function that you wanted to learn was a classification function, then what you really wanted to do was to learn the classification boundaries between the classes. So here, for example, if you wanted to learn a classification function that gave you a value 1 inside the double pentagon and 0 outside, then you wanted a function that would paint everything inside those pentagons red and everything outside blue. But what the function you learned really was the figure to the right, where I've plotted the output of the function along the y-axis and the input on the horizontal plane. So you wanted it to give you a value of 1 inside the pentagons and 0 outside. Now, in this example, we've sort of assumed, the way I plotted it, that all of the red dots lie within the pentagon. All of the blue dots lie outside. And so you could actually learn this function that would sort of pop up and become a 1 just inside the pentagon and 0 outside. In reality, what you're really going to see in the real world is your data are never so cleanly separated. And what appears to be the red region, you're going to see some blue dots. What appears to be the blue region, you're going to see some red dots. Maybe there are some fuzzy boundaries where you sort of transition over from the red to the blue. So the function you really want to plot, although ideally you might still want to learn a function which computes what we have to the left, the raised double pentagon, at the edges. What you actually see is going to be fuzzy. You're going to see things sort of kind of go over from one side to the other. So in the two-dimensional example, here's a trivial, very much simpler two-dimensional example where you want to classify dots as either being blue or red based on their position. So the kind of training data you would get, the kind of function you want to learn is something like the one to the right, which is a step function, the simplest function that you can think of, not something complicated, which is that you've got a horizontal, you've got a hyperplane, you want everything, a discriminating hyperplane, you want everything to the right to be assigned a value 1, everything to the left to be assigned a value 0. So the actual value of the function is going to be a 0 until the hyperplane, then it rises up and then becomes a 1 on the other side of the hyperplane. The data you will get ideally would be all, would have a output value of 1, a target value of 1 on the one side of the function, and the target value would be 0 on the 0 side of the function, ideally. In practice, what you will get is something like what you have to the right, where you're going to have a few dots suspended on the blue, red dots suspended on the blue side. Why is it suspended? Because you're actually seeing dots whose target value has been given as 1, but they're actually on the blue side of the figure. Similarly, you're going to have some blue dots lying on the floor to the right side. And they're lying on the floor because they've been assigned a target value of 0, but they are on the one side of the figure. So, and it is from this that you now have to learn this little function. And as you can see, just having these dots on either side confounds the issue, because now it's no longer clear exactly how you're going to plot the plane. Now, even before beginning to worry about how you're going to plot the plane, perhaps it makes sense to take a step back and see what all of it really means. So I'm going to go back to this one-dimensional example that we saw very early in class. This is just for visualization. So the input is 1D. In reality, of course, the input is going to be many-dimensional. But here, we're still assuming that you have a classification threshold. It's a simple classifier. The input is 1D. The data have, what was that? A target value of either 0 or a target value of 1. So all the blue dots have a target value of 0. All the red dots have a target value of 1. Now observe that the class data are no longer separable by a simple linear classifier. In the case of when the inputs are one-dimensional, what would a linear classifier be? Anyone? It's just going to be a threshold, right? In 2 dimensions, a linear classifier is a hyperplane. In 1 dimensions, the classifier is going to be a threshold. So when I have data of this kind, there is no simple threshold that's actually going to separate out the blue dots from the red dots. Do you guys playing with your phones mind turning them upside down and placing them on the table? So can you shut the phone, please? Yeah. Turn it upside down if you don't mind. Right. So in this case, you don't really have a simple threshold that can separate the blue dots from the red dots, right? Now, if I did, nevertheless, in theory, I could always learn a function which learns exactly this relationship. If I have a complicated enough network, I could learn something of this kind. But is this really what we are trying to learn when we have data of this kind? Not really. You're not trying to pick and satisfy every single point in your training space. And in fact, it's very easy to see that this doesn't even begin to make sense. Now, why does this not begin to make sense? Consider this situation. I've given you training examples, and then I have some training examples So I have a set of different training examples which all have the same input value, the same x. But some of them have a target output of 0, and some of them have a target output of 1. So now at the same point, you have both red dots and blue dots. What must the function compute? What would you want the function to compute at this point? Not only are the data not separable, the data are actually naturally confounded. So if you have something of this kind, let's say I have in my training instances 90 red training instances and 10 blue training instances. So in this case, what would you want the function to compute? Would you want it to compute a 1 at that point? Pardon me? Neither of these. Ideally, you would want to say you wanted to give the average. You wanted to compute. You wanted to tell you something about the distribution of the data. So what you really want is to compute something like this: the probability of 1 given x. Because this is much more useful than a simple 1-0 decision. When I just give you a 1, I'm hiding the fact that sometimes you get a 0 at that point. If I give you a 0, I'm hiding the fact so that sometimes you get a 1. So you begin to see that having a unique answer doesn't even really make the most sense. You want to indicate, if you want to actually indicate the nature of the data that you learned the function from, having it predict probabilities makes a lot more sense. But then, let me do this very simple thing. I'm going to, so everybody with me so far? Right? And you see why this makes sense. But now let me just do this. I still have the same red and blue dots. They're not at exactly the same position. One of them is 10 raised to minus 13 off to the right from the other. Now, does this minuscule shift of the red dots with respect to the blue dots warrant a function that just goes up and down? It doesn't. Just nudging things by a little bit shouldn't actually change the value of this function. Shouldn't change the desired target function so grossly. You'd still want this to say that around this value of x, on average, 90% of the points that you see have the value 1, 10% have the value 0. You would still want this to compute an output probability, the probability of 1 given x. And so, given this, let me go back to this situation here. Without the overlapping points, right? Actually, let me go ahead. How can I, if I concede that at each point a minor wiggle shouldn't actually change the output of the function, then you're sort of conceding that at every single value of x, what you really want is the probability of 1 given x. But then your training data don't really give you confounding values all the time. If you actually look at your training data, if you look far out to the left, you aren't going to see any reds at all. The whole thing is going to be kind of somewhat scattered. So how do you sort of come up with a target function in this case? Because simply considering the target value assigned to the training data isn't giving you the entire story. It turns out that your training data are not complete. Your training data are telling you part of the story. The real story itself must be inferred from the training data. So let's try to do this slightly differently. Let's look at each training point. Let's look at a small window around the training point and compute the average y value within that small window. So that is going to be a reasonably good estimate, approximation, or an estimate of the probability of 1 given that particular input. And here, there really aren't, if you look at this plot, we've seen this before, there really aren't any values which are 1. So the average value remains a 1. As I keep sliding right, at this point, I've seen my first little red. And again, if that window, the narrow window within which I was looking, had become very small, the whole thing was going to go back down. So you get this business of worrying about what the nature of the window is and how many training points you're actually going to see. But if all works well, as you slide from left to right, you're going to see in the beginning a few points of the wrong class, and then their density keeps increasing. Eventually, the wrong class becomes the right class because they begin to dominate. And then when you go far enough out to the right, all of the values that you see in this case are going to be 1. And so the blue dots represent your guess at what fraction of training points at that training instances at that particular value of x would have the value 1. And that is going to be given by this sequence of blue dots. I can connect them all up because, again, these blue dots, you really don't have blue dots. They're not training instances. They're mythical. I'm just sliding a window across the input. So what you're really plotting is something of this kind, a complete function. And this is a story that you have inferred from the training data before your first guess as to what the function must be. This has nothing to do with neural networks. This is the story that the training data are telling you. And this is really what you're trying to compute. Now, if I had to compute a function that had this value, what would that function be? We're very familiar with this. So what function computes this now? Sigmoid. The sigmoid, right? What nature of sigmoid? There are a couple of different sigmoids. We've seen a tan H, and then we've seen the logistic function. So this would be, what would this be, Manira? This would be the logistic, right? So, and this has the logistic. Now observe, by the way, those of you who ever wondered what the difference is between a tan H function and a logistic function, they're actually the same function. A tan H is just the logistic slid half a point down and scaled up. And you can prove this mathematically. So it's exactly the same thing, right? So the logistic function, we know the nature of the logistic function. The logistic is not the only function that you could have fit. You could have pretty much fit any function that takes the shape. The moment you plot a logistic on it, what we are really imposing is a model. This is our model for how the probabilities vary from the left to the right. But then imposing a probability model of this kind is not unusual. Anytime we deal with estimating probabilities, estimating distributions, anytime we deal with statistical models, we are going to assign a model like a Gaussian or a Gaussian mixture or a Laplacian or a multinomial. All of these are models. In this particular case, the specific model that we are choosing is the logistic function, the sigmoid, right? So, and this one, the logistic function, clearly has this value. Class 1 becomes increasingly probable as you go from left to right. So here is your logistic perceptron. That's a sigmoid perceptron with a single, here in this case I have a single input, and then I have a bias W0. So it's just going to be 1 over 1 plus e raised to minus W0 plus W1x. W0 is basically capturing the position at which the function goes from being from predominantly 0, where the function goes from modeling a probability that predominantly represents the value 0 to producing a probability that represents the predominance of 1, right? So now that was for one dimension. If I had two-dimensional input, here's the kind of input you have again. You have the red dots suspended on the blue region, the blue dots lying on the red floor. No single hyperplane is going to separate the two. But if you were trying to learn a logistic function for this kind, again, the same principle applies, right? But when I'm applying this principle, what is it I'm actually considering? I'm not looking at every point. So here is something that you really, why do I even call this a linear classifier? So remember when I was plotting, are we all out of chalk? Somewhere here there are pens. Yeah. So now in the one-dimensional case, we had all of these points, and we were looking at little windows and plotting our function. in the two-dimensional case, what are we looking at when we compute the fraction of ones that we must consider as the target output? Pardon me?
Spheres or 3D?
Not quite, yes. Go ahead. So what you are really considering is, if I have something of this kind, this is my function. This is going on to infinity, this is going on into infinity. It's a strip that is at a distance. You're taking a little strip, and the only thing you're considering is the distance from the hyperplane. And you're taking this little strip and walking across the space and saying what fraction of values within this strip has the value 1. So it's not a, right? Because the only thing that you're interested in is the distance from the discriminating hyperplane. So, and that's exactly what this little function is going to compute. When x is a 2D variable, this function is going to compute the distance from the discriminating hyperplane. And the sigmoid itself, observe, is now, although it has this function where you're looking at a weighted combination of all of the inputs, in reality the weights represents a vector that's orthogonal. It's orthogonal to the discriminating hyperplane, and the argument of the exponent is just the distance from this hyperplane. That's all you're really computing. But the basic idea remains the same. So, Abhishek, yeah, right. So now let's go back and look at how we would actually estimate this model. Now, having established that all we are really interested in is the distance from the hyperplane, I can go back and still use my one-dimensional example because it really is the same thing. What I'm calling x over here is now going to be the combined distance from the hyperplane, right? So I'm now given a collection of training instances, x, y points, and I need to estimate the weights for this guy. And how would I do this? Now, this red line represents the probability of seeing a 1 at any value of x. What would the probability of seeing a 0 be? It's going to be just the mirror image around the halfway point. So that's going to look like so, 1 minus this guy, right? Or I'm going to use a +1 -1 notation just for representing the target value, but when I plot it, I'm going to be plotting either a 0 or a 1 because the curves represent a probability, and the symbol value, the target value, can be anything, right? +1, +0. So I'm going to use +1 and -1 for mathematical convenience. So if I write it like so, then the probability of y equals 1 given x is given by the sigmoid, right, which is 1 over 1 plus e raised to minus w0 plus w1x. The probability of y equals -1 is 1 minus this guy, which ends up, if you work it out, being 1 over 1 plus e raised to plus w0 plus w1x. So if I use a +1 -1 notation for y, if I simply multiply this term by y itself, I get a common representation for both of these guys. So if I plug in a +1 over here, this becomes this equation. If I plug in a -1 over here, this becomes this equation, right? So I just have a common representation for both of these probabilities. And now given this, let's see how I can actually learn this. I've given you some training data, x, which is a collection of x's and y's, and I'm going to use a maximum likelihood estimate. So when I'm using a maximum likelihood estimate, what am I really doing? I'm computing the joint probability of all of my training data, and I will try to maximize this joint probability. So I'm going to compute the joint probability of all of these xy pairs, assuming they're independent and identically distributed. That's simply the product of the probabilities of the individual xy pairs. And I can use Bayes' rule to factor it out. P of x comma y is P of x times P of y given x. Correct? P of y given x is given by our logistic function. And then I have the P of x. So this is what I'm going to try to maximize. correct? And let me just manipulate that a little bit. So here's what we've got. The term on top is the joint probability of all of our training data. Now, when I'm trying to learn the parameters of my model to maximize the probability of the training data, I could equally well use it to maximize the log probability of the training data, because the logarithm is a monotonic function. And so if I take a log of this, that simply becomes the summation of the log of the probability of x minus, because the key component of the logistic is in the denominator, the sum over all the training instances of the log of that term in the denominator. And this is the log likelihood of our training data. And when I want to learn this parameter, I'm actually going to try to maximize this guy. I'm going to try to maximize the W0 and W1, which is basically telling me the intercept where the logistic crosses over from favoring 0 to favoring 1, and the rate at which the logistic itself rises, which is given by W1. I'm going to try to learn these to maximize the log likelihood of my training data. And when I'm maximizing the log likelihood of the training data, I observe that the first component over here, summation of log of p of x, is not a function of w itself. So all I really need to worry about is the second component. So the second component had a neg minus, so maximizing the log likelihood is the equivalent of minimizing the negative of the log likelihood, which is the term we have on the top. And guess what this is? This is simply the Kullback-Leibler divergence. This is simply the cross entropy that we've been using to optimize our neural networks. So if all I had was a simple perceptron, and I used cross entropy to learn the parameters of this perceptron, what I'm really doing is learning a statistical model using the maximum likelihood criterion. So if you wondered what the entire backpropagation process with the cross entropy criterion was doing, it was really a maximum likelihood estimator for a probability model. Everybody with me so far? Yes. So now let me go to a slightly more complex figure over here. Nonlinear classifiers. We've been looking at a linear classifier. I have a nice linear decision boundary. What about this guy? This is clearly a nonlinear classifier. And what am I really doing? First, let's consider this nice clean case when the reds and the blues are cleanly separable and the network must learn to compute the function to the right. Furthermore, I'm going to assume that my network is sufficient to compute the function to the right. And we know that the network that's sufficient to compute the function to the right can be one such network is the figure I have here. I have two subnets. The first subnet is computing the first polygon. The second one is computing the second polygon. The final neuron is taking an OR of the two. So this is a sufficient subnet. By this time, everybody knows this for a certainty, right? Let's look at the subnet. What about this guy to the top? What is that neuron to the top? If I'm just using, let's say I'm using simple logistic functions or perceptrons, right? If I'm if I'm considering perceptrons, that neuron to the top, is that a linear classifier? Is that a, speak up? Yes. Who else thinks that that perceptron to the top is a linear classifier? Yes, raise your hands. Is it a linear classifier or not? Please. Yeah. It's a perceptron, right? Just a threshold function. It's working on the affine combination of its inputs, and it's comparing it to a threshold, right? Now this is a key point. The reason I want you to really get this and raise your hands if you got it, and not raise your hands if you didn't, is that I'll spend an entire class explaining to you that it's a linear classifier. If you haven't got it, that's a threat. So. So if you got this, raise your hands, please. Everybody, 1, 2, 3. Right, it is a linear. Andrew, did you get it or not? Yes. Yes, okay, thank you. So what is the implication of having this be a linear classifier?
Tell whether if it's within the pentagon.
Yes, but what does it mean about the inputs to this final perceptron? They must be linearly separable, right? So what is happening over here, if I consider this, the output of the network right here, at that point, expect them to have a form like this, like the figure to the left. Otherwise, I would not have been able to separate the dots out from the red dots out from the blue dots. So what does this tell me about the rest of this network? Everything below that final perceptron. What is the rest of this network doing? Yes. I'm assuming that you are looking at me and not at the slides. You cheat, right? But if you didn't, and you had to take a guess, what would you say it was doing? It's transforming this very nonlinear figure that we started off with, and it's modifying the input space such that the two classes became linearly separable.
So is it very similar to what an SVM is doing in projecting into a different space world and just learning the space that separates it?
You are sort of predicting what I'm going to say, right? So the rest of the network is just a transformation that transforms the data from the non-linearly separated classes at the bottom to the linearly separated classes at the top, right? And that's beautiful. You have this really complicated looking machine, and its entire purpose in life is to make things separable. So what this means is, if I've got linearly separated classes, why do I need a perceptron? I can use pretty much any linear classifier on top. I could use, for instance, a support vector machine on top, right? So this is true of any sufficient structure. Nothing special about this. However, if I have an insufficient structure, something that doesn't have the capacity to actually separate the two classes, in that case, what is the lower box going to be computing? What would it be trying to do? See, the final perceptron is still a linear classifier. So everything else at the bottom is going to try to make the data as linearly separable as possible, to the extent possible. So here is the magical bit of it. Even if your network is insufficient for the task, it's still going to try to move things around. It's a transformation, it's a nonlinear transformation of the space that tries to make the data, the classes, as linearly separable as possible, so that you can finally learn a linear classifier which almost does the job, right? So mathematically, now, one way of thinking about it is, you can think of this as having an SVM with slack variables on top, right? And now you're permitting some slack, and then you're learning the rest of the network. You're learning the features on which the SVM could work, right? I mean, just as a slightly twisted way of looking at it. So what we are saying mathematically is that the network has two components. Everything from the beginning till the penultimate layer is a function f which converts the input space into a feature space where the classes are maximally linearly separable. And then the final perceptron is just going to try to classify, separate it. But then that final perceptron was a logistic. What was it computing? It was computing a maximum. It was a maximum likelihood estimator for the probability of one given x. So what is the entire network now actually doing? The entire learning process is simply a maximum likelihood estimation process. We are learning simultaneously for a very ugly function, which we have magically transformed into two components. One, which learns a feature space which tries to separate the data, and the other, which tries to actually fit a probability model on it. Now, it's kind of pretty, right? When you go back and think about it, a classification MLP actually comprises two components: a feature extraction network that converts the inputs to linearly separable features, or nearly linearly separable features, and a final linear classifier that operates on these nearly linearly separable features. Questions? No? So that means, for example, that I could just use a SVM at the output, right? It doesn't have to be a perceptron. I could have a perceptron with a margin. So if I wanted to use an SVM at the output, how would I do it? What would the options be? One thing is to just train my regular MLP. And then when I'm done training the MLP, I have a feature computation network function which makes my classes linearly separable. Having done so, I can go back and get all conservative and train an SVM with a perceptron. And that should, in theory, work better than should be more robust than your original classifier itself, right? Alternately, you could actually sort of factor in the margin during the training process. And some of you who did homework 2 have already encountered one such model, which was that. The angular loss, angular softmax was doing something exactly of this kind, right? So if you see where the whole thing comes from, right? So fine, we know what the entire block until the penultimate layer does. What about the lower guys? How do the lower layers respond? So obviously the entire network has many, many layers. It has many, many components which are also sort of twisting and turning some knobs and modifying your input space. But somehow in the process, they are converting these classes into being linearly separable. So what exactly do these lower layers do? What would you expect to see as you went from layer to layer to layer? So you have something called this manifold hypothesis, which says that when the classes are linearly separable, when the classes are non-linearly separable, it's like saying that they are linearly separable on some non-linear, possibly disconnected manifold, right? In other words, I can take the surface that they live on, and twist and mangle the whole thing, and I can do that through some really ugly nonlinear transform. And when I'm done with that, the entire thing is going to live in a new space where the classes become linearly separable. And so you would expect that as you go through the network, these classes actually become increasingly linearly separable. So to illustrate that, here's this little figure. This is a toy example. We're trying to train a network to separate out the blue from the red. Now this is almost a circular decision boundary. It's ugly, and it's definitely not linearly separable. So the figure to the top left shows the mean squared error. Here we've used the mean squared error as our training objective. You could replace scale with MSE. And we're going to plot that as a function of iterations. Now the bottom, it's got only 2 layers. It's a 2-3-1 network. So it has 3 hidden neurons. That's it. And so the bottom left, remember, you're taking the input. You first compute an affine transform, and then you apply an activation to this affine transform. So you've gone from 2 dimensions to 3 if it's a 2-3-1 network. The affine transform, the first affine transform that you compute, actually is going to take this entire sheet and put it in 3D space. And so the figure to the bottom middle left is the affine transformed data. And then the figure to the middle right is what happens after you apply the activations. And then the figure to the bottom left is going back from 3 to 1 dimension, because it's a single output, right? And it's an affine transformed version of what you see in the middle right. And basically, if it's a single classifier at that point, you're applying a threshold through this affine transformed combination. So this affine transform combination is now going to be a scalar. A linear classifier is going to be a threshold, right? And the bottom right is the actual decision boundary that you finally get. So when I initialize my network, obviously it's not learning the decision boundary for the circle. But then observe what happens. Something crazy happens, right? If you look at what happens just before this final classification has happened, eventually, when you get to the classification layer, what it does is it puts the thing in 3-dimensional space, it raises the blue, it pushes the red down, and then when you project it down to one line, all the blues are on one side, all the reds are on the other side. And now we can apply a threshold. So it's basically transformed this whole space by moving it up, twisting and warping the space until the classes became linearly separable. Andrew, yeah? Yeah, so I'm going to do that for something more complex. This is CIFAR 10. You have several classes, and this was a fairly deep network, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 layer network. When I initialize the network, here are the outputs of all of the various layers. So basically, it hasn't really learned anything, right? But then as I go through the training process, observe what happened. When I get to just below the final classification boundary, all the classes are linearly separable. Now in CIFAR 10, the data are almost perfectly linearly separable. You can see that so here you have a high dimensional space. I'm projecting it down to 2 dimensions in this case. So they still kind of look mangled. What you're really getting is a twisting and turning and warping of the space. And as you go through the layers, you can see that the classes become more and more and more linearly separable. In fact, out here, they're already linearly separable. The rest of the layers are just pushing them further and further apart. And finally, you get these things properly linearly separable at the end, so that you can actually apply a linear classifier. Same thing in 3D. Here's what it looks like, where I project it down to 3D. And you observe that what it does, it's pushing some classes up, some classes down, pushing them aside, but it's warping the space, and it's doing so progressively through the network until the classes become linearly separable. So it's and there's nothing magical about MLPs. Pretty much every type of network that you've seen so far is an MLP of some kind, right? A convolutional network is an MLP that scans. A recurrent network is an MLP that just keeps repeating the same process. And all of them are doing the same thing. Now, that was for separable data. What if the data are not separable? This is a more typical setting for classification problems. This is what we began with, right? In this case, you have some blue dots on the red side, some red dots on the blue side. So what exactly happens? Here again, the feature extraction layer is now going to transform the data such that the posterior probability can now be modeled by a logistic. So what happened was we actually fit a logistic to the final layer, or a softmax. We are enforcing the nature of the probability distribution that we're going to use to compute the posterior probability of y. So the learning process is naturally going to sort of warp the data and the feature space such that the probability distribution that we have decided is going to the model that we have decided is going to represent the probability distribution actually does a decent job of capturing the posterior probabilities. So if you had inseparable classes with an output logistic perceptron, then the feature extraction layer is going to take all of this data and transform it to something like the figure to the right. And now it's going to fit a logistic perceptron. And so if this was, this is for linearly separable data. If it's non-linearly, if the boundaries are not linear and they're still not separable, if the boundaries are linear and they're not separable, you're going to learn a posterior probability. If the boundaries are non-linear and they're still not separable, then the lower portions of the network are going to try to transform them into some space where you can fit a logistic and have distance from a linear boundary be indicative of the actual probability of the class, right? Having said all this, how many of you have read this book? It's an old one. So it's a very nice book called Illusions by a guy called Richard Bach, who was very famous in the 80s. And this is about a reluctant messiah who writes a book. And the last page in the book says everything in this book may be wrong. So everything I've said so far might be wrong, right? Because what's to stop me from learning something of what I've got to the right? If I throw a sufficiently detailed architecture, I can separate pretty much any arrangement of points. So when I do this, what does it actually mean? What does it mean when I've trained a network which does this horrible job? Overfitting. I've learned that I still have a probability distribution. I'm still learning a statistical guesser, so to speak. It's just that I over-parameterize my statistical guesser, and so I'm getting rubbish. But the basic concept itself still stays the same, right? Questions? I'm going to switch to a different topic. Changing gears, okay? Now let's go back, and we've looked at what the network actually does from one perspective. You can think of it as a two-component function. The first component comprises just the output layer, and that output layer's job is to compute the posterior probabilities of the classes if you're doing a classification network, or to compute whatever other function that it's trying to compute. And the rest of the network is just a transformation that modifies the input space such that the output function can actually work appropriately on the input. And so we've seen what the network learns here. We've seen how it transforms the space. But then, what can we say about the manifolds? We've said that it's kind of modifying the input space and just warping the manifolds till the classes fall into the kind of structure that we really want them to be. But can we say more about it, right? So let's go back and recall the basic perceptron. This was the basic perceptron we had. We've seen this before. If I just had a single perceptron with a threshold activation function, then what is the perceptron really doing? It's looking at the inner product between the weights and the input, and it's firing if this inner product exceeds a threshold, right? So we've seen this before too. In high dimensional spaces, all vectors are pretty much the same length. The inner product is effectively indicative of the angle between the weights vector and the input feature vector. So the weights vector now actually ends up representing the archetypal pattern that the perceptron wants to see. And what you're really doing is computing the angle between this weights vector and the input. And if the angle is less than a threshold, the perceptron is going to fire. Otherwise, it's not going to fire. So although I've been speaking about this in terms of distances from a plane, it's equally valid to say that if I were thinking of a logistic, it's really telling you the probability of an angle for the class, right? Which means it's the decision boundary is in the nature of a cone. So, but again, this also means that the perceptron is really a weighted, if you think of it in terms of the thresholds, the perceptron is really a correlation filter. It's computing the correlation between the pattern represented by the weights and the input. And if this correlation exceeds a threshold, it's going to fire, otherwise it doesn't. So if I wanted to build a single perceptron which looked at this LED kind of pattern that I have, and its job in life was to detect if the input was the number 2, then if I asked you what the weights are going to look like, without even batting your eyelid, you should be able to tell me that you expect the weights themselves to represent a 2 pattern. And what the perceptron is really doing is computing the correlation between the input and this 2 pattern of weights. And if that correlation exceeds whatever threshold you set for acceptability, it's going to fire. So if you had something like the figure in the middle, the correlation between the red dots and the blue weight dots to the left is only 0.57, this one's not going to fire. If you have something like the green figure to the right, that correlation is much higher, it is 0.82. So the perceptron will fire, right? Now, this is for a single perceptron. What would happen if the network got more complex? In this case, let's say the perceptron's job was to look at these LED patterns, the network's job was to look at these LED patterns and tell you if the input was a digit or not. Now, before we began speaking of this, we were speaking of this abstract space where I would take this entire LED pattern, which has, how much is it, 7 times 4, 28 pixels, and think of this as a 28-dimensional space, and we were working off this 28-dimensional space. And instead of working off this 28-dimensional space, let's look at a more semantic interpretation of the data itself. So if I think of it in a more semantic sense, then you expect the lowermost layer of perceptive neurons in my network to capture key features about the input, which will distinguish the presence of digits from the non-presence of digits. So digits you would typically expect are going to be composed of these little half lines. And so you'd expect to find detectors for little horizontal lines at the top, horizontal lines at the bottom, horizontal lines in the middle, vertical bars to the left and the right. But you'd also expect to see other kinds of patterns. For example, you never see a diagonal line in one of these digits. So you might also expect to see something like diagonal lines. If that fires, it's definitely not a digit, right? So the lowermost layer of neurons end up being feature detectors. And the rest of the neurons are just combining these features. So what you might see over here might be the second layer of neurons might just be combining these lower layer detectors. And one could say, oh, I found the number 0. Another could say, oh, I found the number 1. The third one could say, oh, I found the number 2. And if I also have perceptrons in the lowest layer which capture definitely invalid patterns, then I could have a perceptron in the second layer which says, oh, I found found invalid pattern, so this is definitely not a digit. And all of these are going to go in and feed into the final perceptron and tell you whether it's a digit or not. But then let's take a step back. What about the first layer perceptrons? The first layer perceptrons have detected features in the input, horizontal lines, vertical lines. So suppose I just took the detections of these first layer perceptrons and combined them back in exactly the same way, right? So let me take all of the outputs of all of the first layer perceptrons. And the first layer perceptron says I found a horizontal line on top. I found a horizontal line at the bottom. I found a diagonal line. So anything that's fired, I take the weights, I take the pattern that it has found, that it was looking for, and compose them back together. What would you expect to see? You would expect to see the input right back, right? Or would you expect to see just exactly the input?
No.
Then what would you see?
Like a combination.
So you are going to expect, because the network is specifically learned to distinguish digits from non-digits, you're going to see those aspects. You're going to get a partial reconstruction of the input, which focuses on the portions of the input that tell you whether it's a, yeah.
And you're assuming you're not able to completely represent them in the intermediate layers.
So basically, we are saying that.
You'd be able to reconstruct them perfectly, right?
But we are saying that if I've just optimized this for the purpose of detecting digits, then you expect the intermediate layer not to have any stuff that doesn't actually relate to the task at hand, right?
Like if we have a network which actually like classifies into 10 classes, then ideally we should, right?
If you have a sufficient density at the output so that all the patterns become relevant, then you would be able to do that, right? So the network here is optimized to recognize digits. We'll only retain distinctly digit-like or obviously not digit-like features, and the rest are irrelevant and are going to be lost, right? So let's try to make it explicit. Let me go back and try to, but you get an idea of what you expect these guys to capture. Can I use that, to my benefit? Let's try to make this explicit. So let me actually say I'm going to try to reconstruct my input from what these guys found. Now observe that I'm putting the same patterns back together. So this is the equivalent of saying that that I have this hidden layer, which is detecting patterns. And then once the patterns are detected, I'm going to put those patterns back together, which is to say that the reconstruction weights are going to be identical to the analysis weights, because I'm just putting everything back together, right? So this is what we will call an autoencoder. If I construct something of this kind, it's taking an input and composing it right back. This is an autoencoder. And the portion that analyzes the input, the lower portion, is the decoder, encoder. the portion that recomposes the input from whatever has been discovered is what we'll call the decoder. The simplest autoencoder is just going to have one single perceptron, right? So consider the case where this one single perceptron has only linear activations. And when it has linear activations, what would be expected to learn? We're going to, let's say I'm using the L2 divergence between what it reconstructs and what we are feeding it. So this perceptron has this job. It's going to read the input. It's going to compute some feature. And then it's going to use that feature to reconstruct the input. And I'm going to try to minimize the error between the reconstructed input and the actual original input. And if the activation is linear, then here's the arithmetic. I won't actually work through this. You're trying to minimize the L2 error between the reconstructed input and the original input, right? So basically you're saying the reconstructed input, I can say because the activation is linear, the output of the hidden unit is just Wx. The reconstruction is W transpose times Wx. So the entire error is x minus W transpose Wx. I'm trying to minimize the squared norm of that error. And if I did that and tried to find the W which minimizes this error, we know exactly what we're going to get. That W is going to give me the principal component of my input. This is just PCA, right? If I have a linear activation. So what is happening is that the autoencoder finds the direction of maximum energy where most of the information in the input lies. And that is the direction. So the hidden unit is going to tell you how much you move by, and you're just going to, and the decoder is just going to put that, is going to give you some scaled version of the what the activation found. So to give you an idea, you're only going to be able to reconstruct a single pattern, which is the weight W, right? So all the hidden unit is telling you is how much that weight W must be scaled by to reconstruct the input. So pretty much every single dot that you get at the output is going to lie along this principal component, which is this blue line. It doesn't matter what the input is, the output is always going to lie along the blue line, right? Because all you're able to reconstruct is a scaling of this weight W. So what this means is that if I got rid of the encoder portion, once I train this, no matter what I fed the decoder, the output is always going to be along that blue line. Because the only thing I can reconstruct is, yes?
So is it's only projecting it along the principal, the first principal?
The first principal component in this case, right? Because you're minimizing the error, and the lowest error is going to be along the first principal component.
And why is it not able to find other components? Is it because we're not, like if you have...
If I had more than one...
hidden units, right?
If I had more than one hidden unit, then I would actually have
the two highest energy.
Yes, exactly. So mind you, although I tied the input weights and the output weights, even if the input and output weights were entirely different, you're still going to just find the first principal component because that's what you're going to do. And of course, getting to your point, if I had many hidden units, what I would find is the principal subspace. Everything is going to, if I had linear activations, right? So this is with linear activations. I don't even have to work out the arithmetic. It makes sense to you that this is the principal subspace, just terminology. Everything until this portion is the decoder, and the blue portion is the encoder, and the gray portion is the decoder, right? Now, the encoder analyzes the data, the decoder synthesizes data, but the decoder can only synthesize data on the principal subspace. It cannot wander outside the principal subspace because that's all it has the capacity to construct. You have a certain number of weights. Those weights can be combined, and you can't actually go off in a direction that is not composed, cannot be composed using those weights. Everybody get what I'm saying so far, right? Now suppose I introduce a non-linearity to this input. So far we were speaking of hidden activations, but now I introduce a non-linearity. What happens when I introduce a non-linearity? We've already seen this. It warps the space, right? So if I'm warping the space and trying to construct the data, what would you expect it to find? And so here's where anybody got a piece of paper that I can borrow? Yeah. Yeah, this will do, right? So this is the kind of, if you had linear activations, you're saying the data basically lies mostly on this principal subspace with some fuzz off the subspace. And what the autoencoder is going to do is to simply capture this principal subspace. But then if you put a nonlinearity, the nonlinearity is permitting the space to be folded. And so now it's going to find a principal manifold which is not necessarily linear. And it's going to try to find the principal manifold along which the data lies with some fuzz off of it. Yes, Wes?
In this decoder step, are we going to apply like the inverse of the activation function?
Right. Or basically, whatever the decoder does. Now, the whole entire thing is driven by the decoder. So you have to realize that it doesn't matter whether the encoder and decoder are the same thing or not anymore, just as it didn't when you're using linear activations. The decoder constrains what you can construct. The decoder is capable of constructing a specific manifold. And the entire learning is going to try to find the parameters of the network such that you find a manifold that reconstructs the input with minimum error. But once you do that, the crazy thing is that the only thing you can construct once you've learned this, regardless of what I feed the decoder, anything I feed in is going to result in some data on this principal manifold. And but of course, the kinds of manifolds I can learn are very much restricted by the nature of the network itself. So if I want to have the ability to learn more and more complex manifolds, I need to have more and more deeper networks, more complicated networks. But eventually, given the right configuration of decoder, not the encoder, right? Although the encoder, you need a sufficiently complex encoder and a sufficiently complex decoder. And the one need not be a mirror image of the other. It doesn't really, although the mirror image makes intuitive sense, right? What you're going to learn is the decoder is going to be able to reconstruct a specific nonlinear manifold. And the entire network is going to learn the structure of the manifold on which the most of the energy of the data lies. And once you do that, regardless of what you feed the decoder, you're only going to construct things on that manifold. But here are the caveats, right? So here's a little two-dimensional example. We have a helix, fuzzy data around a helix. And there's only one, if I were to choose only 1 degree of freedom, then you'd say that the data really are helix plus noise. So you'd expect the decoder to actually learn the helix. And now observe that on my training data, at that central point, I'm going to see some range of values, right? So over here, out here, I'm going to see some range of values in my training data. Once I've trained it, I can just behead this, take just the decoder, and I can feed it input outside the range of values that I saw in the training data. And if my structure that has been learned is proper, if I go outside the range of data that has been learned during training, it should continue to construct a helix, right? That's not what actually happens. You get these, here I have too much noise. So you can see those purple dots are what it actually learned. So you're beginning to see that this theory kind of breaks down in practice unless there's not sufficient, there isn't that much noise. So here if I make the noise really small, it begins to kind of learn stuff. If I'm trying to learn the sinusoid to the right, then if we gave it data from the left half of the sinusoid to learn the sinusoid, and then when you try to extend it to the right, it doesn't actually learn the sinusoid. It goes off and continues to be straight. So there's stuff to be taken care of. I mean, the theory is right, the idea is right. The point is this, although these are so-called universal approximators, they don't always learn anything beyond what is really in your training data, and that continues to be a problem, right? Nevertheless, here is something really cool that falls out of this. So if the hidden representation is of a lower dimensionality than the input, you get the equivalent of a nonlinear principal component analysis, although not really, as you saw, because this is very much regulated by how good your training is. And in the next class, we will see how we can try to improve the ability to capture the structure of the data, right? So it learns the manifold of the data if properly trained, but assuming it is properly trained, then something really cool happens. The decoder can now only generate data that on the manifold that the training data lie on. So the decoder has learned the structure of some particular manifold. This manifold represents the training data. So if I get rid of the encoder, no matter what I feed the hidden layer, this layer in between, what the decoder generates is going to lie on the manifold that the training data actually relying on, right? So this means that if it's properly trained, it actually becomes an excellent generator for the distribution of the training data. What do I mean by this? Suppose I learn this properly, and now I want to create synthetic versions of synthetic data which look like the class of training data that I've seen minus some fuzz. I could just take this decoder and feed it all kinds of inputs. And whatever the decoder generates must, in theory, look somewhat like the training data, right? So the decoder is now a generator of sorts. It's a dictionary for the training data. It's capable of generating data of the class that the training data themselves belong to. And so what we get is that if I excite just the decoder, you get a source-specific generative dictionary, and exciting it will produce data that are typical from the source. So for example, if I were using these LED patterns to train the decoder, I would expect that if I excited the decoder, what comes out is, if it's not digits, it's something that looks like parts of digits or plausibly digits, right? Let's see if, whether we can actually put this to use, whether this theory even begins to make sense. I'm going to try this for a very simple problem. So here I'm going to try, in this example, we fed an autoencoder of this kind, and this is a fairly deep autoencoder with many, many layers for the encoder and the decoder, music from a saxophone. And now, when you take the decoder, if you've trained it properly, then it's only capable of generating spectrographic representations of saxophone notes. Not saxophone notes, but stuff that could be produced from a saxophone, which could be combinations of notes or any such thing, right? And so now, Aldo?
How can you tell the domain of this function? As in, you're exciting those inputs, right?
Yeah.
But how can you tell the domain of
I've trained the complete autoencoder using just a music from a saxophone.
Yes, and then you're going to, if I'm getting it right, you're going to feed something.
So I've trained it using a saxophone. Now the decoder should, in theory, have learned to produce stuff on the manifold of saxophone sounds, right? Now, no matter what I feed it, what it outputs is going to be on the saxophone manifold.
My question is on the part of no matter what I feed it. So what are you feeding it?
Any odd number, right? So remember, this is here. I have this network. And at this point, when I give it a valid input over here, it's going to compute a bunch of numbers. And those numbers are being fed downstream, and that results in the production of saxophone notes, right? But there's no need for me to only feed it numbers that are produced from some input over here. I could give it pretty much any odd input, could I not?
Yes. So it's just random numbers?
I could give it anything, and so in this case, I've literally just triggered this with a 1 in the first position and zeros elsewhere for this particular example, and see what sound it produces, right? And if someone else had a question, yes, sir?
So before, when we're talking about the digits, the way you trained that part of the network was that you trained a classifier, and then you
No. So this is just an autoencoder at this point. This is not.
So how do you train that then?
So the autoencoder is going to try to match the output to the input, just like PCA, right?
Yeah. Thanks.
So when I do this, here's what it produces. Let me see. This was trained on a saxophone, right? I give it some random input. It sounds somewhat like a saxophone note, right? Not a note, but some child doing horrible stuff on a saxophone. Or this one. This is what you would be doing if. So it's actually learned. It's not producing white noise. It's not producing random stuff. That's my point, right? What it is producing is saxophony. Is it? Okay, let's see, right? I'm going to.
As long as it picks up what you think is saxophonic.
Well, so we shall see, right? Here's something I did with a. Sounds different from what he's got the first time around, right? Well, if you don't believe me, since I expect skeptics in class, I'm going to put these things together in a little more complex application, right? And this is entirely for your benefit, not for mine. And because I had a student who wanted to write a paper. Now, we're going to try to separate mixed sounds. So I have sounds from different sources. And given a mixed sound from multiple sources, I want to separate out the sources. So here's a standard dictionary-based mechanism for this. You try to learn a dictionary or some machine that is only capable of producing sounds from one source. So for example, I could learn a dictionary for the guitar, right? I could learn a different dictionary, say, for the drums, which is only capable of producing drum notes. And now when I get some mixed sound, I'm going to say, how do I excite my guitar dictionary and my drum dictionary so that when I sum the two, the output sounds like what I've got. And once I've done that, then I can go off and just pull out the stuff to the left and pull out the stuff to the right. I expect that the left path will be producing guitar sounds, and the right path will be producing drum sounds, right? In theory. And now I've just shown you this famous autoencoder, which learns about clarinets and saxophones. Let's see if it actually does the job. So when I'm separating stuff, yeah, that's all the theory. Okay, so here's what we're going to do. I'm going to learn an autoencoder for different sources, for the different sources. So if I were trying to separate, say, guitars from drums, I'm going to learn an autoencoder that for guitar sounds. And my hypothesis is that if everything is learned properly, then the decoder portion of the network, when excited, is only going to produce guitarish sounds. It's not going to produce white noise. You do concede that when I learned it from the clarinet, the output wasn't right? I can assure you that no matter what you try, you're not going to get white noise. You're not going to get speech-like sounds. It sounded like something, maybe a bad clarinet, but it definitely didn't sound like, a completely, a chicken, right? So, using that idea, I can now have a dictionary, this decoder, an autoencoder trained from one source, and now the decoder is only capable of producing sounds on the manifold for that source. I can do the same for the other sound as well. And if I train an autoencoder on the second sound source, that decoder is only capable of producing sounds on the manifold for the second source. And now if I give you a mixed signal, I flip things. I'm going to ask you, what is the input I must provide for each of these two decoders such that when their outputs are added, it sounds like the sound that I just got, right? And how would I estimate this? How would I estimate the inputs? Anyone?
You retrain the decoder, right?
Pardon me?
You retrain the decoder.
I'm not retraining the decoder. The decoders, everything is fixed. I've frozen it because now I want a decoder that can only generate sounds for the first source, a decoder that can only generate sounds for the second source. The question I'm asking is, how do I excite these decoders? Because different excitations are going to produce different points on the manifold, right? Different types of sounds for those particular sources. I can use backprop, can I not? I have a target output, backprop, nothing changed. There's nothing magical. Backprop can learn parameters, it can learn, given an output and a network, it can learn the optimal input, and it's all the same problem, right? I'm not trying to learn the separation, I'm trying to perform the separation. So in the sense that I have these two decoders. The first decoder, if excited, is going to produce sounds of the first kind. That is my hypothesis. The second decoder, if excited, is going to produce sounds of the second kind. That is my, right? So if I give you an example of a sound, and I'm going to ask you, how do I have to excite this decoder to produce this sound? That means I can use backpropagation to find the optimal input for the decoder to produce that output. Andrew? Right? Munira?
So you would just randomly initialize the input and then use back.
Just use backpropagation, right? So I basically just use separation to do exactly that. And then the output of the individual decoders are, in principle, the sounds that I want. So let me see if this works, right? Two instruments, both wind instruments, wind or string, whatever. And now, here's what went in when I produced this mixed sounds. And here's what it thought. And here's what it thought the second sound was. So just to illustrate, right? The intuition we were trying to convey seems to kind of hold up. Now, not to get too fooled, I cherry pick my examples. Right? If you expect this to happen every single time, no, it's not going to happen. But as an illustration of a concept of what the network is actually learning, what these manifolds mean, and how we can actually use this for our own purposes, you get the idea. I'll stop here. And the next class, we'll continue with this business of trying to learn the appropriate structure for these manifolds and trying to use these now to explicitly model distributions of the input. But if you have any questions, I have a minute. No, thank you.